Welcome to the course on linear algebra. I've been really excited to make this course for a long time because linear algebra is probably the most important math right now. Whether you're a statistician like myself, a physicist, a researcher in any scientific discipline, a computer scientist, a mathematician, an engineer, you have to know linear algebra because it's just that important. And we'll talk about why in this series. I have noticed that I think that there are two dominant ways in which linear algebra is usually taught. One is a geometric perspective, and the best example of this is 3 Blue, 1 Brown series, The Essence of Linear Algebra, which I recommend checking out. It's good for building some foundational intuition. And then there's what I like to call the procedural or the algebraic perspective, and a good example of this would be David Lay's textbook, Linear Algebra with Applications, which is usually the textbook for an undergrad course or an engineering course in linear algebra. It's the one with the satellite on the cover. Both of these perspectives have pros and cons. And I aim to keep the pros of both and try to get rid of some of the cons, because both of them have one big glaring weakness in common, which is that both perspectives completely fall apart once you get to what would typically constitute the latter half of a linear algebra course, which involves abstract things like vector spaces and proofs and all kinds of things like that. And I aim to be different by emphasizing statements, logic, and reasoning, which sounds way worse than a geometric or algebraic perspective, but I promise you there's reason behind it. And I think that by emphasizing statements, logic, and reasoning earlier, I think we'll avoid the fall off that you get in most linear algebra courses when you introduce these abstract concepts. I think we'll be more prepared for them when they come up. I don't think we're going to be as lost. And I think that this is a good way to connect the geometric to the procedural perspectives, giving you kind of like a best of both worlds approach. So I do have a textbook that I recommend. It's Linear Algebra and Its Applications by Gilbert Strang. This is probably the best example of trying to do both. And I also recommend checking out his MIT OpenCourseWare course. It's really good supplementation. I'm going to get a lot of practice problems from this textbook. I'm not really going to be taking a lot of material for the lecture from the textbook, but coming up with practice problems is kind of annoying, so I'm going to pull a lot of problems from the textbook. So without further ado, let's just jump right in. And in order to meet my goal of emphasizing statements and logic, I think it's necessary for me to tell you what a statement is. So in mathematics, we're particularly interested in things called declarative statements. And a declarative statement is a statement that can either be true or false, but can't be both. So here are some examples. This is a statement: the sky is blue, the sky is red, 1 equals 1, and 0 equals 1. So these first two, the verbal ones, they're either going to be true or false, but whether they're true or false kind of depends on the context. For instance, the sky is blue, you could say that's a true statement, but that's only true during the day and during clear skies in most parts of the world. The sky is red is usually going to be false, but that could be true during like a particularly potent sunset, for example. And so the truth value of these statements depends on things like the weather, the time, the year, your geographic location, but they are always going to be either true or false. So they're declarative statements. Now these statements, these over here, these mathematical statements, these are special because this statement 1 equals 1, it doesn't matter where you are or what time it is, or nothing matters. This is always true. And a statement that is always true is called a tautology. And analogously, this statement is always false. It's 0 equals 1. That's never true. And a statement that is never true, no matter what the context is called a contradiction. So a lot of the business of a real mathematician is trying to show that some new statement is equivalent to a statement that we already know to be true, like 1 equals 1. And if you can show that, then you're showing that that new statement is true. And so that's how you make progress in mathematics. It's how you show new things. There's a existing foundation of things that we know to be true. We know to be essentially equivalent to 1 equals 1. And then if we could show that something new is equivalent to one of those things, then we kind of expand out our bubble of knowledge. Or if we could show that it's equivalent to 0 equals 1, then we can show that that's not true, and we can kind of branch out like an amoeba going in different directions and seeing what's true and what's not. And that's what a mathematician does. And in this way, a mathematician is not really like a computer. They're not crunching numbers and trying to do a bunch of arithmetic. They're more like a lawyer, I guess, like looking at all the facts and trying to see what is true under different assumptions and in different contexts. And so that's how we're going to try to look at linear algebra. And the way we're going to do that is we're going to start by introducing some operations, because right now we just have statements. They're either going to be true or false. The next thing that we need are some techniques to manipulate those statements and make new statements that might be more useful to us and allow us to solve problems. So suppose we have some statement like this: a quantity equals another quantity. This is either going to be true or false. And we also have some number n. And so I'm also going to start introducing this mathematical notation. Saying n is any real number is exactly the same as writing this here. The symbol means is an element of, and this fancy r is the set of real numbers. So this is the exact same thing as saying n is a real number. It's just a lot shorter, and mathematicians tend to prefer this, myself included. So suppose we have this statement of equality, and we have some real number n. The first thing that we could do is if we take this statement and we add any real number to both sides, it's going to produce an equivalent statement. So I hope that that is obvious. This should feel obvious. If I have 1 equals 1 and I add the same number to both sides, it's going to still be true. If I have 1 equals 0 and I add the same number to both sides, it's still going to be false. And so adding the same number to both sides is going to produce an equivalent statement. And multiplying both sides by the same number. Multiplying both sides by the same number is also going to produce an equivalent statement for the exact same reasons. Again, this should just feel very, very obvious. We're not doing anything fancy yet, but we'll show how these very simple operations will let us solve like 8th grade math problems. Now, the next one is going to be probably the silliest, but if I just take this statement and I move it, I bring it down here, I hope you'll agree with me that this has not changed the statement in any way. This is completely equivalent to the original. It's just over here instead of being up there. So again, that's going to feel very silly. It's going to be very obvious, but this third operation, I'm going to call it rearrangement. Rearrangement. So now we have our statements, and we have these 3 operations we could do to produce equivalent statements. And again, I'm sure all of this feels very obvious, but these 3 operations actually lie at the heart of linear algebra. We'll see some examples of that. There's just one more thing I want to introduce, which is statements with variables. So maybe in a formal logic course, you may have to quantify what these variables represent, but this isn't a formal logic course, so I'm going to just say right now that unless otherwise stated, variables in this course are going to represent real numbers. So we can have a statement with variables such as x plus y equals 3. And the truth of this statement, again, it's only going to be true or false, but the truth of this statement is going to depend on the values of these variables. For instance, if x is 1 and y is 1, this is going to be a false statement. And if x is 1 and y is 2, then this is going to be a true statement. So with that out of the way, I think we're ready to actually look at some, I'm going to say problems, but really we're just going to have multiple statements together, and we're going to see the consequences of that. So what happens when we have 2 statements involving 2 variables? So here's an example of that. We have x plus y equals 5 and x minus y equals 1. And I want to make an assumption here, and that assumption, I'm going to put this in a color because this is important. This is an assumption we're making. And the assumption is that we're going to have the same x and y in both of these statements. So the assumption implicitly that we're making here is that there exists an xy pair that satisfies meaning makes the statement true, that satisfies both statements. And what this assumption allows us to do is to treat the x in this equation as the same x in this equation. And that's going to be important because I want to show you what we can do with those 3 operations that we just discussed. And so if you remember, one of those operations was we could add the same thing to both sides of a statement, and it's not going to change. It's going to produce an equivalent statement. So that's what I'm going to do. I'm going to take this statement here, and I'm going to add the same thing to both sides. So on this side, I'm going to add x plus y. And then on this side, I'm going to add the same thing. I'm going to add 5. Now 5 is the same thing, and we know that because this statement tells us that x plus y is equal to 5, meaning they're the same thing. So I'm going to take this statement, and I'm going to add to it the same thing to both sides, and as we just discussed, that's going to produce an equivalent statement. And that equivalent statement is going to tell us, as long as these are the same x's and the same y's, that 2x is equal to 6. And now I can take this statement and I can manipulate it again. I'm going to multiply both sides by the same thing. This time I'm going to multiply both sides by 1/2, and this is going to produce an equivalent statement. But this equivalent statement is going to tell us that x is equal to 3. And so this is what I meant when I say we're producing equivalent statements, but these might be more useful to us. This is actually telling us the identity of one of these variables. And so this is more useful than this original statement, or even both of these original statements, but it's equivalent to both of these original statements. If we have both of these statements are true, then it's equivalent to saying that x is equal to 3. And that's what's interesting about math. We get there from there. So it's cool. Now, we could take this fact that x equals 3 is equivalent to this combination of statements, and we can just put that identity of x into one of these statements, and I could say that 3 plus y equals 5, and that tells us that y is 2. Because we add the same thing to both sides, we add -3 to both sides. And so we use these techniques of manipulating statements in ways that produce equivalent statements to take this set of statements and from it produce the equivalent set of statements x equals 3 and y equals 2, telling us something more useful, telling us the identity of these numbers. So I hope that's an interesting example. I know this is like a very simple 8th grade math problem, and honestly this one is too, but I just want to show you that it can get more complex than that. Here I'm going to do the exact same thing. The numbers are just going to be uglier. And so I'm going to take this statement. I'm going to take this statement first, actually. And I'm going to produce an equivalent statement by multiplying both sides by the same thing. I'm going to multiply them by 5. I'm going to get 5x plus 5y equals 25. And then I'm going to take this statement, and I'm going to produce an equivalent statement. I'm going to add the same thing to both sides. But this time, on this side, I'm going to add 5x plus 5y, and on this side, I'm going to add 25, which I know to be the same from this statement right here. So this is going to give us the equivalent statement, 12y is equal to, what was this, 43. And then I'm going to multiply both sides by 1 over 12 to produce the equivalent statement, y is equal to 43 twelfths. And then I can plug this identity of y back into either one of these statements, but this one on the top looks easier. And that will give us the equivalent statement again, that x plus 43 over 12, or 43 over 12 is going to equal, I'm just going to write this as 60 over 12. And then, from here, we just add the same thing to both sides, -43 twelfths, to get the equivalent statement that x is equal to 17 twelfths. And so again, we just walk through the same series of steps, and now the numbers are uglier, but it doesn't really matter. We take this set of statements, and from them, we take operations, we apply them very carefully so as to produce equivalent statements, and we produce the equivalent yet arguably more useful statements, x equals 17 over 12, and y equals 43 over 12. I want to pause and just emphasize the main idea of what we're doing here. The point of linear algebra, and I guess mathematics in general, is not to be able to solve these ugly problems with gross numbers by hand. A computer can do this type of stuff instantly, so that's not the idea. The main idea is to realize that this set of statements here contains exactly the same information as this set of statements. Nothing was added, nothing was lost, and we only took steps that we knew produced equivalent statements. Those steps transform the information into a form that's easier to interpret. And that's what mathematicians actually do. You start from a complicated description and you move using only safe, deliberate, and logical steps to an equivalent description that makes the meaning more clear. Mathematics is not about computation. It's about rewriting information without changing what it says until its consequences become visible. But it's not always going to work out like that. And so now we need to talk about what can go wrong? Because the best way to understand how something works, one of the best ways is to look at where it falls apart. So I want to look at two things here. So let's see what happens if we try to take our same set of reasoning that we've been using, and I want to take this set of statements and I want to produce an equivalent statement from them. And so what I'm going to do is I'm going to do what I originally did. So I'm going to take this, I'm going to produce an equivalent statement by multiplying both sides by the same thing. I get negative x minus y equals negative 5. I'm going to multiply by negative 1. And then I'm going to produce an equivalent statement here by adding the same thing to both sides. On this side, I'm going to add negative x minus y, and on this side, I'm going to add negative 5. I know these to be the same from this statement here that tells us this is equal to this. Now, when I add these together, I get the equivalent statement, 0 equals 1. And this is it's just not true. It's false. And so I'm showing that this set of statements, from them, I can produce an equivalent statement, which is a contradiction. It's something that's never true. And so what does that mean? Well, in order to figure out what it means, let's try to figure out what went wrong and where it went wrong. So one idea could be that there's a problem with the statements that we use, but I can't really see why that would be the case. These statements are fine statements. Their truth value is just going to depend on the value that these variables take on, but in isolation, either one of these is fine. The next place where a problem could arise could be in these operations that we've done. This idea that we can multiply both sides by the same thing to produce an equivalent statement, or add the same thing to both sides to produce an equivalent statement. Well, there's not really anything wrong with that either, because that just stems from the definition of equality. That stems from what makes two numbers equal. So there's nothing really that could have gone wrong there. So I encourage you to try to pause and think and see if you can come up with some reason of why this might have failed before I tell you. So hopefully you've done that. But actually, where it went wrong was in this step, which we may have forgotten about. It went wrong with this assumption. In order to do this step right here, in order to add these things together, we assume that this is the same x and this is the same y. The x and y that satisfy this statement, we assume that they are the same x and y that satisfy this statement. We make that assumption, and that allows us to cancel these x's and cancel these y's. It allows us to combine like terms because we assume that they are the same x and the same y. That assumption is what's wrong. This assumption is the thing that is not true, because if there is an x and y that satisfies this equation, then it cannot satisfy this equation. And I guess one way to see that is if x and y add together to equal 5, they can't add together to equal 6. It's kind of obvious with these two statements. And so this assumption is false. And when we make this assumption, we produce an equivalent statement that tells us 0 equals 1. So it's equivalent to saying that this assumption is a contradiction. So actually what's wound up happening is by walking through these steps, we've shown that this assumption is equivalent to a contradiction, which means that we know this assumption is not true. We've effectively proven that there is no x and y that satisfies both statements. It doesn't exist. And the way we prove that x and y doesn't exist is by showing that this assumption is equivalent to a contradiction. This is, again, key idea in mathematics. Now let's look at what else could happen here. So I'm going to take this set of statements on the right, and I'm going to go through our same procedure that we've been following. So I'm going to multiply this one by a constant to produce an equivalent statement. I'm going to get negative 2x minus 2y equals negative 10, just multiplying by negative 2. And then I'm going to add the same thing to both sides of this equation to produce an equivalent statement. Negative 2x minus 2y, and then on this side I'm going to add negative 10, which I know to be the same as negative 2x minus 2y from this statement here. And what do I get? The resultant statement that I get is I get 0 equals 0. And this is always true. So this is a tautology, and it's a little bit interesting. What is really going on here? I encourage you to pause and think about it. But what we're doing is we make an assumption that there exists some x and y that satisfies both statements. And in some cases, what happens is that making that assumption led us to new information. It's the same information, it's equivalent information, but by making that assumption, that tells us that x has to equal 3 in this case, for example, and y has to equal 2. Under these set of statements, under this set of constraints, this must be the case. But in this case, adding this additional statement here didn't really give us any new information. If some x and y satisfies this statement, then it must also satisfy this statement. And I will tell you that the reason that's the case, I mean, the mathematics shows it because we find that we get a tautology. If we just say, oh, there's an x and y that satisfies the first one, we can go through some algebraic manipulation to show that we add that to this equation and we get the same, we get 0 equals 0, which is always true. But an even easier way to show it is to just take these rules that we've already done. If I take this equation here and I produce an equivalent statement by multiplying both sides by 2, I get 2x plus 2y equals 10, which is this statement here. They're the same, they're equivalent statements. And so this tells us that if there is an x and y that satisfies this equation, then it must also satisfy this equation. This is not a contradiction, it's implication. This is called implication in logic. All right, I'm going to touch on a few more things in this video here. The first one being what happens when we add even more statements and even more variables. Well, with the geometric perspective, when you have 3 variables, things get really complicated, which I'm going to show in a second. But with a logical statement perspective, we can just do what we've been doing. And so let's see what happens here. I'm going to produce an equivalent statement by multiplying both sides by -2. I get -2x minus 2y minus 2z. 2z equals -16. And then here, I'm going to produce an equivalent statement by adding the same thing to both sides. I'm going to add this to the left side and this to the right side, which I know to be the same from this statement right here. The x's and y's will cancel, and I get -z is equal to -7. And that tells us that, and then I could get an equivalent statement by multiplying both sides by -1. I get z equals 7. And then I'm also going to produce an equivalent statement to the first one, but this time I'm going to multiply, actually I'm not, I'm just going to leave it as it is. And then on the bottom here, what I'm going to do is I'm going to add the same thing to both sides. On the left, I'm going to add this, and on the right, I'm going to add this, which is the same from this first statement here. And so I'm going to add x plus y plus z here, and here I'm going to add 8. And the x's cancel, the z's cancel, and I get the equivalent statement for y equals 9. Now I'm going to multiply both sides of this statement to get an equivalent statement that tells us y is equal to 9/4, just multiplying by 1/4. And now I can take any one of these statements, but it looks like the easiest is going to be this top one here. And I'm going to plug the information that these statements give us back into that one to hopefully get a new statement that tells us something new. I'll get x plus 9/4 plus 9/4, and then I'll write 28/4 instead of 7. And then I'm going to tell us that this equals 32. What's 8 times 4? 32/4? I think that's right. And then from here, it's just basic arithmetic, which I'm ironically very bad at, but I think, oh god, let me think. 9 and 28 would be 37. So 32 minus 37 would be -5/4. I think that's right. I'm gonna have to cut here and make sure. Okay, I just paused to double check everything, and yes, I think this is correct. So we walk through the exact same set of procedures. We only manipulate these statements in ways that we know produce equivalent statements, and from this set of statements here, and the additional assumption that there is some x, y, and z triplet that will satisfy all 3 of these equations, we found the equivalent set of statements, x equals -5/4, y equals 9/4, and z equals 7. We have veritably solved the 3x3 system. I think next time I will probably try to solve these systems before making these problems, so I see that they come out to cleaner numbers. But the next thing that I want to talk about is geometry, because the geometric perspective is not like it's not like it's useless or anything. I want to show how useful the geometric perspective is, especially in lower dimensions. And so I want to take our earlier statement, and so that would be this one right here, this x plus y equals 5 statement from earlier. And I want to plot that on the Cartesian plane. And so that's this plane here. And so you're probably familiar with this. If x was equal to 1, then y would have to equal 4. And so I go to 1, I go to 4, I put a point there. If x is equal to 2, then y would have to be equal to 3. And I'll put a dot there. If x was equal to 3, then y would have to be equal to 2. And spoiler alert, if I plot all of these things, or all of the values that make this statement true, it's going to be all the points on a line in two-dimensional space. And so any point on this line will satisfy the statement x plus y equals 5. And so because of that, I want to make the point here that this geometry is a consequence of the statement. It's not the other way around. Everything doesn't necessarily depend on geometry. We have a statement. The statement is either true or false. And when you plot all of the points that satisfy that statement, that make that statement true, they happen to form a line. And so we can represent these statements as lines in two-dimensional space, but that's just because that's what it looks like when you take a Cartesian plane and you plot all of the points that make this statement true. It happens to make a line. And so now what I want to do is I want to plot all the other statements from earlier. And if you remember, when we applied our operations to produce equivalent statements with this first one, we got a value of x and a value of y. We got an equivalent set of statements that told us what x and y were. When we did this one, we found that we got a contradiction, and when we did this one, we got a tautology. So I want to visualize all of those ideas right now. So I'm going to move this up here, and then I'm going to plot all of these points. I'm going to plot all these points. So when I plot the first statement here, how do I get this? There we go. When I plot this first statement here, we have x minus y equals 1. So x, if that was equal to 1, then y would have to equal 0. So that would be right here. If x was equal to 2, then y would have to equal 1. And so that would be right here. And if x was equal to 3, then y would have to equal 2. And so that would be this point right here. And if I plot a line through all those points, I will try. It'll look something like that. Something like that. So that's that first statement. Now let's do the next one. If x was equal to 1, then y would have to equal 5. And so it'll be right there. If x was equal to 2, then y would have to equal 4. So x is 2, y is 4. If x was 3, then y would have to equal 3. And it's going to produce a line like this. Like this. And finally, let's do the last one. If x was equal to 1, then y would have to equal 4. And so that's going to be this point here. And if x was equal to 2, then y would have to equal 3. And so that's going to be this point here. And what do you know? It's actually going to be the same line here. So I'm just going to draw this, try to draw it in a way where you can see both. But all the points on that line are going to be on the other one. And so the point here is not to use geometry as a tool to, make you understand. This is just a way to visualize it. Each of these lines represents the set of solutions to that statement. And so in the first case, when we only had the yellow line and the blue line, the yellow statement and the blue statement, we found that by going through all the operations that produce equivalent statements, we found that led us to the equivalent set of statements that x must equal 2, or x must equal 3 and y must equal 2. And that's this point here. It's the intersection on both those lines. It's right here, the intersection. And so that tells us that if there's a statement that satisfies one, or if there's a set of x and y that satisfies one statement, like the yellow one, if it's on that yellow line and it's on the blue line, then it must be this intersection here. And with the red statement, we found that we got a contradiction, which says if there's a point on this yellow line, if there's a solution to that yellow statement, then then it cannot be on the red line because these are parallel lines. And so if there's a solution to this yellow statement, it can't be a solution to this red statement. And the visualization of that is lines that never intersect. And for this green statement, when we go through the plotting, we find that we get the same line, which means the set of points that satisfy this yellow statement is the exact same set of points that satisfy this green statement. You can see that when we plot this in two-dimensional space. So hopefully that visualization makes it easier to understand. We're plotting the set of solutions to these statements, and with the blue one, we find we get one solution that satisfies both statements. The green one, it's an infinite amount of solutions. It's the same set of solutions. And the red one, there's no set of solutions that can satisfy both statements because, as you can see with these lines, they never intersect. But it's just because if there's an x and y that add to 5, it can't also add to 6. It's not possible. The best thing about this geometric perspective, though, is that it gives us the intuition that with these 2x2 sets of systems, and in general with any set of systems, there's only 3 possibilities. You either have one solution, an infinite amount of solutions, or no solutions. And that's kind of easy to understand with the lines because they're either going to be parallel, the same line, or they'll intersect at a single point and then go off in different directions. It's kind of easy to see that with straight lines, that's the only possibility. You can't have 2 solutions. It's a lot more difficult to see in higher dimensions, and we'll probably walk through some proofs of why that is the case. But with these systems of equations, if you have in statements and in variables, then there are only 3 possibilities. You have one solution, no solutions, or infinitely many solutions. And I hope that this geometry kind of makes that intuition easier to understand. All right, so the last thing I want to talk about in this video is why I don't generally take a geometric perspective. So in 3 dimensions, statements are going to look like planes. If we consider this statement x plus y equals 5, but we plot it in 3D with the third z variable, then the value of z doesn't really matter because, for example, the x, y, z triplet 3, 2, and 10,000 is still going to satisfy the statement that x plus y equals 5 because x plus y equals 5. It doesn't matter what z is. And so when we plot that in 3-dimensional space, we have the line of solutions where x plus y equals 5 plotted on the xy plane here, the xy plane here. And then z is allowed to vary. It could be any positive or negative number. So it produces this flat plane that extends forever in the positive and negative directions, but intersects with the xy plane on the line that's given by the same line that you would get if you plotted x plus y equals 5 in 2-dimensional space. And so these statements look like planes. And I went ahead and I tried to plot the planes that we would get from the set of statements that we used in the 3x3 example, and it looked like this. So this obviously won't do. This looks horrible. And this took me like 15 minutes to draw. So I'm not an artist. You can tell from my handwriting that I'm not very good at making these pictures. Software exists that can do this for us. So I have Desmos, and I just plotted the 3x3 system in Desmos. And there's a few things to point out. So each one of these planes is the set of points in 3-dimensional space that satisfies the respective statement. So if I make the statement x plus y plus z equals 8, all the points on this red plane here satisfy that statement. And the same goes for all the other planes. So the point that we found when we took this set of statements here and we produced the equivalent set of statements, x equals -5/4, y equals 9/4, and z equals 7, if I remember. I guess I don't need to remember. It's this point right here. And visually, that is going to be the point that's on every single one of those planes. And so this purple point right here is the only point that lies on the green, the blue, and the red plane. Also, we can look at intersections of planes as lines. So you can see like the blue and the red plane intersect on this line here. I can't really see, I guess the green and the blue plane probably intersect on a line that looks like this, which is kind of similar to the line that I guess the other line would look something like this. It's probably behind the blue one. I don't know. But the point is that these two planes, they intersect at lines in three-dimensional space. And so you can get a visual intuition from this geometry, but even in 3 dimensions, I have to use software. 3 Blue 1 Brown, like the king of geometry in the geometrical perspective, he wrote a whole Python coding language. I don't know if it's Python, but he wrote a coding language called Manim that's specifically designed for making those nice math video visualizations. But it would take me like 30 minutes, even with ChatGPT, to make like a 15-second visualization. So it's a lot more work. So I recommend checking out his videos just because they're interesting. It's also a lot of work that goes into making those videos, so it's very easy to appreciate. But as you go to dimensions beyond the third, trying to visualize things even with software becomes borderline impossible. You would need like a 3-dimensional picture that's constantly changing. You add that fourth component of time, and then intersections are less obvious. And then beyond the fourth dimension, it's impossible. So you need different applications. Almost always you're going to need more than 4 equations. And linear algebra and this idea of taking this perspective of, oh, I'm going to treat all these things as statements, is going to make it easier to seamlessly go into higher dimensions. There's no difference between these statements in 3 dimensions as there are the statements with 2 variables that are in 2 dimensions. There's no difference. And so that's why I'm trying to take this statement perspective. So in the next video, we're going to introduce matrices and show how they simplify this stuff that's already pretty simple. And then we're going to discuss an algorithm for solving arbitrarily large systems that's called Gaussian elimination. Thank you all for watching. I hope you enjoyed. I hope this was interesting, and I hope it helps you understand the subject.